Basic Calculus Part 4, Rate of Change. The derivative is a function's rate of change. So therefore the derivative f prime of x is the gradient of the tangent to the curve of f of x, or the rate of change of f of x. Means the same thing. We divide the change in y by the change in x to see how much we're doing, how much the y is increasing per unit of the x value. So rate of change of g of x equals 3x plus 5. Well, this is a straight line graph. So it's increasing uniformly. If we differentiate, we get g of x equals 3. What that means is that between any 2 points, let's say we go a change of 1 in x, then it means a change of 3 in y. Because it's 3, 1. Change in y, 3 over change in x, 1. If we change the point and have a change of 2 in x, correspondingly, we'll end up with a change of 6 in y, which is still a ratio of 3 to 1. Rate of change is y over x. Speed is kilometers over hours. Acceleration is kilometers per hour over hour. Let's have a look. Rate of change of f of x equals x squared minus 5x plus 4 is 2x minus 5. Now notice it's a curved graph, so the gradients don't always have the same gradient, and that means it has a variable rate of change depending on the value of x. When x is 0, the rate of change is negative 5, which means the gradient of the tangent is negative 5. When x is 1, the gradient of the tangent is negative 3. There it is. When x is 2, 5, the rate of change is 0. There we are. It's the gradient of that horizontal line. And when x is 3, there it is there. When x is 3, then we draw the tangent, and the gradient of that tangent is 1. Always substitute 3 into f prime of x, and we also get 1. Let's have a look at a real life situation. Balloon is being blown up. The volume of the balloon is calculated by the formula 4/3 pi r cubed, where r is the radius of the balloon. The radius is changing because the balloon's been blown up. Therefore, the volume is changing because the radius is changing. Calculate the rate of change of the volume with respect to the radius. dv by dr. Rate of change of v with respect to r, dv by dr. Well, there's v. So we differentiate, and it's 4 pi r squared. At what rate is the volume increasing when the radius is 1? Well, there's the rate of change of the volume. Substitute 1 in, and we get 4 pi. Stone drops from a tower 160 meters high, and its distance traveled in meters is described by the equation s equals 10t squared, where t is the time in seconds. So however far it has dropped is given by that formula, dropped from the 160 meters. So find an expression for the stone's speed. Well, there's the distance, and speed is rate of change of distance, so therefore we must differentiate distance with respect to t. There we are, which gives us 20t. The acceleration is rate of change of speed. Well, there's the speed, so we must differentiate it. And there's dv by dt, the acceleration. The speed of the stone after 3 seconds. Well, there's a formula for the speed of the stone, so we substitute 3 into it, and we get 60. When it hits the ground, well, there's our formula for the speed. That we need to know t, but we don't know t. So how do we find t? Well, distance traveled, s equals 10t squared, where t is the time, and we want that 10t squared to be 160, because as it hits the ground, it will have traveled 160 meters. So that's what we're going to do. We don't know the time, so we're going to put 10t squared equal to 160, and when we solve we get 4 seconds. In pure maths we'd say plus or minus 4 because we have t squared equals 16, but this is a time, so we don't put minus. Now we substitute that into the formula. Notice there, question mark, 1020t. So now we're going to put that for t, and there's our 80 meters per second. Per means divide. So meters per second means meters divided by second. So we're just writing it with a negative exponent. This is the way it's usually written. Stone thrown vertically. Displacement S equals 20t minus 5t squared. That would mean displacement from the ground, how high it is. Velocity of the stone, well, there's the displacement, so we differentiate. So therefore our velocity 20 minus 10t meters per second. At what time will it reach the top of its flight? Well, consider you throw the stone up, slower, 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 it stops and then it comes down. What's its speed at the top? Well, it stops. So speed is 0. So we must put speed equal to 0 to get the time for the top of the flight. There we are. Speed equals 0. 20 minus t, 10t equals 0. Solve for t. 2. What is the acceleration A of the stone? Well, speed is rate of change of displacement. Acceleration is rate of change of speed. So there we are, dv by dt. Differentiate that, we get minus 10. Why negative? Because it's being pulled downwards as it's moving upwards. It's decelerating. But that's a form of acceleration. How high will the stone reach? Well, there's how high it goes, and we know it's 2 seconds that before it reaches that. So we just sub t equals 2 into that formula, 20 meters. How high will it be at 1 second? Well, there's the formula, substitute 1, 15 meters. How fast will it be traveling when it's at a height of 8,75 meters on the way down? Well, that gives the height from the ground, so therefore that must be 8,75. So let's put displacement equals 8,75, 8 3/4. Now we're going to have to solve that, and it's a quadratic equation. We get down here, factorize, and t equals a half we've crossed out. Why is that? Oh, because that's on the way up. This says on the way down. You see it goes past 8,75 meters twice. The height it will reach is 20 meters, so it goes past 8,75 on the way up, and then on the way down. On the way up it goes at 3.5 seconds, at half a second, so on the way down 3.5. How fast will it be traveling when it's at that height on the way down? Well, there's the time, so let's substitute time into the velocity. Negative 15 meters per second. So it's 15 meters per second negative because the displacement is reducing at that stage. Some exercises. Pause, do them yourself first. Okay. Find its speed. St, where s of t equals 3t squared, so speed will be s prime of t 6t. So at 1, we're going to substitute 1, 2 we substitute 2, 3 we substitute 3. Stone falls from the top of the tower, 180 meters high, motion described by st equals 5t squared. Calculate the speed after 1 second, 2 seconds, 3 seconds. Well, that's its motion, that's displacement, so therefore we have to differentiate first, s prime of t, 10t. Now we can substitute those values in. Time taken for the stone to reach the ground, well, that means distance equals 180. So we put 5t squared equals 180. T squared is 36, t is 6, not plus or minus as it's time. Now we want to know the speed when it hits the ground, so we just substitute that 6 into the speed formula. There we are, 60 meters per second. Distance still to be covered by a runner in t seconds is given by that. So it's the distance still to be covered. So the more t goes, the smaller that distance gets. Find the speed of the runner after 1 second, 2 seconds, 3 seconds. Well, if the distance still to be covered is that, then whatever the speed the distance still to be covered is reducing, that's the speed he's running at. So we just differentiate that. And minus 2, that's the change of the distance still to be covered. So his speed will be 2 meters per second. How long does the runner, after how long does he reach his destination? Well, distance to be covered will have to be 0. So therefore we can put it equal to 0. Oh, that's from the other one still. Oh, speed after 1 second, 2 seconds, 3 seconds. All right. We hadn't finished this one. So now we just substitute 1, 2, 3, and it's a constant, so it's going to stay the same. Right, now let's get this onto this one I was so keen about. After how long does he reach his destination? Well, this is to be covered equals 0, so we put that equal to 0. We get t equal to 6. So therefore, after 6 seconds. How fast are you running when he does so? Well, he's running at a constant speed. So, 2 meters per second. 4. Distance covered by a ball rolling down an incline given by 3t squared. Expression for the speed. Well, once again we differentiate. ds by dt. S prime of t, notice that this notation I'm using, it means ds by dt. It's just a useful shortened notation. So 6t. The speed of the ball at 2 seconds, well, we're going to substitute 2 in. And we get 12 meters per second. Acceleration of the ball as it rolls down the slope. Well, there's the speed. So we now differentiate that. And we get 6 meters per second per second. So 6 meters per second squared. Does the acceleration of the ball change as the ball runs down the slope? No, because it's constant.